Homework 16, page 211. We are jumping back to chapter 4. So we're in 4.1. Number 13, 17, 19, 21, 25, 31, 33, 35, 41, 45, 47, 51, 53. Don't miss these. 55, 57, 59, and 61. It's a lot. It's not hard stuff. You'll see what we're doing today. I was going to just barely touch on 4.1, and then we were going to jump into 4.3. But I figured, let's just take our time. Everything today can be said really, really quickly. But I figure, you know what, let's just take our time. We're in no rush here. So it'll probably be better if we just do this. But what we're about to do today is going to be very intuitive if you've been paying attention. So let's begin. Here's a function. What type of thing is this? What type of object is this? Parabola, right? Okay. So polynomial, in particular, it's a parabola. If you graph it, it's a parabola. And we want to find the minimum value of f.
So it's like negative.
Yeah, you remember? Okay, so here's the thing. If you graph this thing, right, it looks like this. And the minimum value, right, this is the place, and you're going to hear me say this a lot, and I've been saying it the same way for years now because of today. This is where the minimum occurs, and this is the minimum value here. So the input is where the minimum occurs. And so up until this point, right, the only type of object that we could find a minimum or maximum value of is a parabola. And that's because of the way we've treated parabolas is, you know, we have this vertex right there. And Noah, you said, where does this vertex occur?
Negative b over 2.
Negative b over 2a. And let's just kind of remember why that's the case. One way of looking at that, one way, is to say, because of symmetry, that has to occur halfway between the zeros. Where are the zeros of a parabola? Well, they occur at negative b over 2a. Plus or minus. And you remember how I said you might want to remember it this way, right? Instead of all over 2a, if you split it up, this gives a nice representation, because what this says to do is go to minus b over 2a, and then you add whatever that amount is to get to that 0. And then you subtract whatever that amount is to get to that 0. The halfway point is right here. Alternately, you could just take these two values, the plus 1 and the minus 1, add them together, and then divide by them, and you would get that right there. It's the average of those two. So the midpoint of 2 points, that's how you do it, right? You find the average of the 2 points. So that's one way of doing it. How did we get this? Well, we took a general parabola, ax squared plus bx plus c. We did some magic to it. That magic was completing the square. And what we ended up with, a bunch of stuff here, but what ended up in here was x plus b over 2a, if you remember. And we said, well, the way that we justified that is indeed, not just, because this doesn't really prove it. You say, how do you know it's halfway between? Maybe a parabola comes down like that and then shoots way back up. It's not, it's symmetric. But the way we did it is we said, well, if you start with x squared, this is just x squared. And then you multiply it by any number a. It'll either stretch it or whatever, or it might flip it down, whatever. But then, if you shift it one way or another, that vertex, of course, is at 0, 0 when you start, but then when you shift it right there, by that much, that would shift it to the if it's negative, right, it would shift it to whatever minus that is, right? So if it was plus 3, it would go to minus 3. If that is plus a minus 3, it would go to plus 3, right? And that's where that negative comes in, right? Everybody with me on that? Okay? And so that's why that occurs. And then whatever that constant ends up being, it either shifts it up or down. But that's where you could tell where that vertex ends up in the x direction. So everybody remember that, right?
Yeah.
Okay, so let's finish this problem here. the algebra 2 way, which is, okay, we know the vertex occurs when x is equal to minus b over 2a. So what is that in this case? X is minus negative 12 over 2 times 3, which is positive 12. How about 6 over 3, which is what, 2? Now what do we need to do? So we found that it occurs at
You plug it into for f.
2, then you just plug it in, right? So then f of 2 is equal to 3 times 2 squared minus 12 times 2 plus 5. That's a 4. 3 times 4 is 12. That's minus 24 plus 5. That's minus 12 plus 5 is negative
7.
Negative 7? Good. Okay, so negative 7. And there's your answer. Okay? And that's great as far as parabolas are concerned. But what if we don't have a parabola? Yikes. We're going to need something a bit more powerful. It won't generalize very well, right? But let's just take parabolas for a second and think about this in terms of calculus. At that point, that minimum point, what's the slope equal to there?
0.
Right. Because, right, the slope, we can see the slope's negative, it's negative, it's negative. This is where the slope is equal to 0, then it becomes positive, blah, 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 blah. So we're looking for the point where the derivative is equal to 0. And if we could find that, if we could figure out what f prime is, set it equal to 0, solve for x, we should come up with that point. So what is the derivative of f in this case?
6x.
6x, right? Because the 2 jumps down, hits the 3, becomes 6. Bring that down by 1, and then what?
Minus 12.
Minus 12. And now we could say, okay, the slope is 0 wherever this is true, and so now we just solve for x. X is equal to 12 over 6, which is just a big fat 2. We plug that guy back into there, and we get the same thing, which is 7. That's kind of cool. Now check this out. In general, if your function is a parabola, it looks like this. And so what's its derivative? 2ax plus b. And if we want to know where is the slope of this thing equal to 0, we would just solve this equation right here. Minus b equals 2ax, and therefore x is equal to minus b over 2a. Whoa, that's kind of cool. I think that's pretty cool. And of course, then you do that and you plug it in and you get out whatever and you find the value of that. And in general, that's what you do, right? Because, and I said in class, right, if you have a cubic, it's not halfway or a quarter of the way or a third of the way between the roots. All bets are off when you have a cubic, right? So like we want to know, you have some kind of cubic function that looks like this. You want to know what's that? It ain't halfway between these guys. In fact, I don't think it can ever be. We could figure that and do extra credit. Prove or disprove that it can never be halfway between a cubic. I don't know, maybe. I think that would be pretty hard to prove, but something tells me that that's not true. Something tells me I've proved that it was not true before in some class or whatever. Okay, so don't just forget anything I ever said about it. Like you can't. It's not that easy. What you do is you take the derivative and you set the derivative equal to 0. So before we move on, we need a bunch of definitions. So, a function f has, here's a bunch of definitions. A function f has a global maximum, and we might not always call it global, a global or absolute. A global or absolute maximum. Those two are interchangeable. If I ever say absolute maximum, it means the same thing as a global maximum. A function f has a global maximum at a number c if f of c is bigger than or equal to f of x for all x in the domain of f. What does that mean? Well, let's just think about a f of x is 1 minus x squared. That thing looks like this. I drew that terribly. That goes through at 1. It would have a global maximum here at 0 because the output, f of 0, is indeed bigger than any other x in it, f of x in its domain. Right? So that's what it means. And this is kind of important. In the domain, so later on in the homework, you might say, like, it might give you something that's like, let's say a cubic does something like this, and it might ask for its global maximum. Well, this doesn't have a global maximum because obviously in its domain. But if you restrict the domain and say maybe this is 2 and maybe this is -5, now you could say what's its global maximum on -5 to 2. Now you're kind of treating this as its domain. You're saying here's a function, here's its, they're going to give you a domain, and then in that case, yeah, whatever that would be its global max. So does that make sense?
Yeah.
Does the definition make sense? Like,
Yeah.
I mean, it's obvious. And like I said, I was just going to say, that's this, let's move on. But, okay. And f of c, whatever you get when you plug it in, is its maximum value. Okay, so two definitions there. A global max at c occurs if f is bigger there than everywhere else. And this equals bothers me. It should bother you too. It's like, well, then, so like,
Yeah.
then, and because that meant, like, let's take sine, then it has a global max here at pi over 2. That doesn't seem very global because it keeps doing it everywhere. But the value is, it's globally, it never gets above this 1. And so that does make sense, I guess. I don't know, whatever. So that bothers me. But I guess it's kind of nice because, well, what if it reaches it again? Well, then you don't need to call it something else. Who cares? Okay. A function f has a global or absolute minimum. Finish it up.
At c.
At c,
If f of c is less than or equal to
there you
f
go.
of x.
F of c is less than or equal to f of x at for all x in the domain of f. And so that was like our example that we started with. It had a global minimum at 2, and f of 2, which was -7, is its f of c is its minimum value. So that value is doing a lot of work there. Or that changes everything. Because if I ask you where is its global minimum, you'd say 2. But if I say what's its minimum value, I'm asking for -7, right? Okay. And what I'm going to do for the rest of ever is whenever I report a, say, minimum value, I'm going to report it like this because that's a lot of information there. Like, then, I really can't fault you if you do that. You know what you're talking about. You knew how to find that, and you knew that that was the place where that output occurs. It's nice to have that all there, right? It's almost like saying, like you're giving me 2 bits of information there, and like this is it. You want to know the input? There's the input. You want to know the output? There's the output. It's nice. So, everybody got these? Okay, so that's global, but obviously, I just drew a cubic, right? It has no global maximum, right? But it still has this thing right here, right? There is a max, and when you're nearby it, if you forgot about all the rest of everything, you'd say, well, that's still some sort of maximum right there. Or as we call it, an extremum. Extremum is like either a minimum or maximum. Singular, it's extrema. I'm sorry, that's a singular. Plural is extrema, which has to do with, which refers to minima or maxima. So, sine has many maxima. It has many extrema. It also has many minima. It has many extrema. Okay, so we're going to use those. We're going to use all this interchangeably. Just getting you used to this. So here's a minimum, but it's not global because it goes here. So we have a word for this too. Here's a new definition for this sort of thing. Excuse me. And so I just want to say one more time, right? We'll say global or absolute if a domain is given. Okay, it might not be for like 1 minus x squared is defined on all real numbers, and it has only 1, and so yes, in its domain of all real numbers, it happens to be the global maximum here at 1. But that also works, like I said, for a cubic, like I've been drawing, right? If we restrict the domain, then we could call it global or absolute. I'm sorry. But what if you don't have a global, but it does have, a function has a local maximum at C if f of C is bigger than or equal to f of x when x is near C.
Yeah.
Okay, and that's just like with the cubic, it's locally, so if you forget that all of that stuff's going on and you just look locally and say, let's pretend that we're nearby that value, then that sure does look like a max, doesn't it? And that's what this is. Okay, and what is x near C? Technically what this means is when x is in some open interval, a to b, that contains C. So like I just drew, you have this type of thing going on. Here's C, where that maximum occurs. Can you draw an open interval around it? Yep, there's an open interval right there. And in that open interval from, say, A to B, is it truly a max? Yeah, right there on that interval from A to B that contains C. Contains C. Yeah, that's what we mean by nearby. It could be arbitrarily small, it could be arbitrarily large. There's no whatever. It's also called a neighborhood. Yep, neighborhood, local. That all kind of fits. A function f has a local minimum
At C if f of C is great, is less than.
at C if f of C is less than or equal to x when x is near C, blah, 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 blah. Okay, everybody got that?
Yeah.
Okay, so let's look at a local max. Okay, so let's say we have this function, f of x equals x cubed minus 3x plus 1. If you graph it, it looks like this. It goes up forever. Now, we want to find, so again, it doesn't have a global max because this goes up forever, obviously, right? Plug in bigger numbers, that's going to take over everything right there and get arbitrarily large. Man, this looks horrible. Give me a second. I'm going to need some more room. I should stand in front of it when I do it. So if you graph this guy, it looks like this. Okay. And so we want to find the local max and the local min. How do you think I do that?
Take the derivative.
n.
set.
There you go. Okay, so I was just joking with my wife a minute ago that like a good math teacher would like for a math teacher would say, take the derivative, set the derivative equal to 0, because that's the answer to many questions. And you'll see as we go on in this class, I'm going to say, okay, so what should we do? And you're going to say, take the derivative and set the derivative equal to 0. And then, of course, we're going to solve for stuff. So, yes, because why is this? Well, we want to know where this point occurs, and we want to know where this point occurs. What are the slopes at that point? 0, right? And so, where does the slope equal to 0? Well, let's find out. So, this is the question we're trying to solve. Where is f prime equal to 0? Well, what's f prime?
3x squared minus 3.
Minus 3 equals. So in other words, we're trying to find out where does 3x squared minus 3 equal 0.
We can cancel the 3.
Yeah, we could cancel the 3, and so let's just do that. Right, we divide through by 3. That's where x squared is equal to 1. And so, x equals plus or minus 1. And that, if you get to this point, you go, oh, therefore x equals 1. Well, obviously, you didn't get the whole story here, right? So one of them occurs at plus 1. The other one occurs at minus 1. What are their values?
Plug them in.
Plug them in, right? So let's plug the 1 in and see what we get. We get 1 minus 3 plus 1, which is minus 1. So we have minus 1 right there. And I'm going to write that as f of 1. Okay, and now the other one is minus 1, and we get minus 1 cubed minus 3 minus 1 plus 1. That's a 1.
Negative 1.
Thank you. Good. And plus 1.
So, 3.
Yeah, oh, that's what I got. Okay, I thought I did it right. Yeah, okay. Thank you. And so that right there, I want to write as f of minus 1. There we go. Okay. Easy. All right. Easy stuff. Take the derivative. Set it equal to 0. You're going to hear that so many times it's going to make you sick. So we have a theorem. We're not going to, and in fact, your book doesn't even bother to prove it because it's like, obviously, just come on, right? It has to be. And so this is called the extreme value theorem. Or we will abbreviate this EVT whenever we use it. So the extreme value theorem says that if a function f is continuous on the closed interval, this is important, on the closed interval a to b, then f attains an absolute max value, call it f of c, and an absolute min value. And obviously I'm abbreviating maximum as max and minimum as min, and that's what I'm going to do forever. Min value, call it f of d, at some numbers c and d which are in the interval a to b. They could possibly be a and b themselves. So let's just draw some pictures and this will all make perfect sense. So that's the extreme value theorem. So let's say we have a function defined on some closed interval a to b. Now let's say it does this. And b. And so again, we're kind of treating this as its entire domain. We're forgetting about everything else right now. We're going to say, okay, then it has an absolute max. Whatever the highest value it is, right? Whatever that is. And that one happens to be the endpoint. And so in this case, the absolute max, the f of c, the c happens to be the b. Okay?
Yeah.
And so, okay, it attains an absolute min down here at f of a. And so the absolute min, the d that happens to be in this interval, happens to be the a value right there. Okay? But, okay, so that's like one possibility. Here's another possibility. Maybe it does something like this. Okay, and sorry. Just wanted to do it this way. Okay, here we go. Boom, boom, boom. Okay, so it attains an absolute max right here at some value in the interval. Let's call it c. It attains an absolute min right here at some value in the interval, call it d. And so you plug in your f of d and you get the value, you plug in your f of c and you get that value. Okay? So that's what the extreme value theorem is. And again, your book says obviously. And it comes down to it being, well, it comes down to a couple things. It being continuous and the interval being closed. Let's see why that's the case. So check this out. There's a bunch of different ways you could do this. I don't think I assigned any of the homework, but yeah, maybe 13 or 17, but it has a bunch of them like construct a function that doesn't do this. And here's the way you do that. So, for instance, if f is, let's suppose that f is not continuous and see how this may or may not fail. Because it might be discontinuous but still work, but we can't guarantee that it will. So here's one way. Here's a discontinuous function that fails to have this property. So here's 1, it goes up, and then there's a hole in the graph. And then it comes down like this and does something like this. And here's 3. Now, it happens to attain an absolute min, whatever that is. Maybe it's a half. Okay? But here, it never, like whatever value this is, maybe it's 3, it never gets there. When you try to plug in the value to get there, like if this is 2, you plug it in, well now you have this value here. And you get closer and closer and closer as you get to 2, but you never take on the value 3 because there's a hole in the graph.
And there's no highest possible.
There's no highest possible one. You might say, well, what about 2.99? Well, go closer. Right? Like,
Still, yeah.
get closer and you can get even closer. And well, if you get closer to 2 here, you'll get closer to 3. Okay, but you're still not there. It doesn't take on that value. Because when you plug in the 2, out pops a, I don't know, 2 or something. Right? So if it's not continuous, and so it doesn't have this property. Now, you might have a function that does this, has a hole here and here. And then it does have the property. So just because it's not continuous doesn't mean it doesn't have the property, but you can't guarantee it because you might have something like this. Does that make sense? That's why it's important that f is continuous. Okay. Now, this, like I said when I first wrote this down, it's important that the interval is closed. Here's an example of how that could fail. Here's an old friend of ours. Let's take a look at this function. This is our friend tangent. And here's pi. Okay, so tangent has no max value on the open interval 0 to pi over 2.
Yeah.
Okay, so the interval's open. Okay, so that's where this breaks down. And so since the interval's open, you can't guarantee it. So it's continuous there because everything like on there, it's continuous, right? On that open interval is perfectly continuous. So yep, we got continuous, but the interval's open. That's how it fails. Because again, it's the same kind of thing. You keep going and you can keep going. Like as you approach, you keep getting bigger. You approach more, you keep getting bigger. And that's the problem with the open interval, is that you can just keep approaching it and your value can just get, bigger and bigger or whatever, right? Now, this is kind of tricky. Here's a closed interval. Here's a closed interval. And so there's pi over 4 up to 3 pi over. Then it's not continuous, right? And so we're seeing this, right? You might think, but I'll cheat it and I'll get a closed interval. Yeah, but then tangent happens to not be continuous, and so this doesn't apply anymore. Okay, and there's a bunch of other ways that you could break this theorem, or a bunch of different examples of functions which don't have one. It's either not continuous or it's this. I've only done a couple, but we could be creative and come up with a bunch of different kinds if we're whatever. But in order to guarantee that it does indeed take on the max and the min, you have to have a continuous function, and it has to be on a closed interval. Okay, everybody got that? Okay, you'll have a few homework questions on that. Okay, here's Fermat's theorem. Not his last theorem. We do not have the time to get into that. You guys know about Fermat's last theorem?
I don't know.
Oh, you haven't heard of this? Okay, so this mathematician Fermat, he went to prove he wanted to show that this only has solutions in the integers. So if you put in a 2 and a 7, right? Let's do 3 squared plus 4 squared equals 5 squared. So when n is equal to 2, you could find integers that make this work. Yeah? Okay. What about if n is equal to 3? Can you find integers to make it work?
Probably.
Maybe.
I don't know.
What about when n is arbitrarily
1,
large?
2, 3. 1, 2, 3 would work. Go we know.
Yeah, and so obviously 1 to n plus 0 to the n is going to be 1 to the n. Yeah, okay. But
Yeah.
that's a trivial solution. Without the trivial solution, can you find any others that work? And Fermat, in his notes, he was writing a bunch of math, because he's a mathematician. And in the margin of his notes, he said he found a beautiful proof to show that this equation has no solutions in the integers when n is greater than 2. I think that's what it is. I could be wrong about this. Look at it if you care. And he said, but I don't have, and it was in the margin of his notes, and he said, but I don't have the room to write it. People searched for hundreds of years for a proof for this, and it wasn't until 1998 or 99, that this guy Wiles, Andre Wiles, I think, but this mathematician finally proved it, and it's way beyond anything I've ever seen. I mean, I can't even begin to tell you. It's ridiculously. And so the idea is Fermat probably didn't have a proof of it. He thought he did, but probably didn't. Anyway, this is not Fermat's last theorem. This is just Fermat's theorem, and it states that if f has a local min or max. Local min or max at C. And if f prime of C exists, then f prime of C is equal to
F of X. Wait.
if it has a max here at C.
Oh, the derivative.
Its derivative there is equal to what?
Is equal to.
Yep. We could prove this. I don't think we need to. Do you think we need to prove it? If you're interested, you could look, the proof is on page 207. My proof is, come on, man. Like, it has to be, right? You could do this rigorously, and you do some stuff, and you say, okay, now I'll let h be some number, and then you have an f of c plus h, and you say, okay, and then the difference from that, and blah, 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 and you could prove it. It has to exist. The derivative itself has to exist. You'll see why if you care. I don't care. I mean, it's obvious, right? Like, we started off with this fact. Now, but be careful, because check this out. What this says is that if you have a local min or max at C, then f prime at C is equal to 0. Do we get it the other way around? If f prime of C is equal to 0, then does that mean that we have a local min max at C? A telltale sign is that, like, I'm asking you, is the reverse true? If the reverse were true, I would have written f has a local min or max at C, if and only if this is true. That's how I would put it up on the board. So when I'm asking you this question, the answer is probably not, like, because you're asking me. So no, this actually, the reverse turns out not to be true. Here's an example. Let f of x equal x cubed. Now, let's take its derivative. What's the derivative of this?
3x squared.
3x squared. Where is that equal to 0?
This is 0.
At 0, right? So f prime at 0 is equal to 3 times 0, which is 0. So its slope there is 0, but it's not a min or a max, because it does this and it does this. So at that point, yes, it's 0, but see what's happening here. Our slope was positive, it was positive, it was positive, and then it hit 0, but it didn't continue on to becoming negative. If it did continue on to becoming negative, then you would have a max there. Similarly here, we're positive, we're coming back, and now, boom. And if, as we continued on, then the slope had become negative, then you would have a minimum. But we have neither of those things going on. Your slope was positive, it became 0, but then your slope became positive again. And if you graph the derivative, you see what's happening here. 3x squared looks like this. 3x squared looks like this. And we're going to get into this, I think, in section 3. Chapter 4, section 3. We're going to go into this in mind-numbing detail. But the derivative has this property that the derivative is positive, right? The slope is positive. Yep, slope is positive. It's getting smaller. Yep, it's getting smaller. It becomes 0. Yep, it becomes 0. But then it becomes positive again. It doesn't go through. Right. If it went through, then you'd have a different story, but we'll get into all that later. So the converse of this statement is not true. Just because your derivative's 0 somewhere, it may not give you a min or a max. It might do something like this. But if your function does have a min or a max, then you can guarantee that right there the slope is 0. And if you want to see a proof, check out 207. Okay? Okay. Now here's another way that this might not work out. So the converse of this is not, or actually a way that you could break this is, so if f has a local min or max at C, and if f prime exists there. So here's an example of one where f prime doesn't exist. F of x is equal to that. And so you say, okay, then its derivative at 0 must equal 0. Well, it doesn't have a derivative at 0. So that obviously can't be true. You can't have an f prime at 0 because that's undefined. You try to take the limit. It doesn't work from both sides, right? We've done this before. You take the limit from the right-hand side and you get a that the derivative is a positive one. You take the limit from the left-hand side, and you get that the derivative is a negative one, and so this does not exist, and so you can't say that it's equal to 0. But, yeah, okay. So, got that? Everybody got that?
Yeah.
I always, you know, whenever you're writing, or reading a new definition or theorem or something, and it says, you know, and this exists, and you're like, of course it has to exist. But, you know, you might lose that point, and maybe you have a question where it's like, okay, what's its derivative at its minimum? And you say, well, its derivative must be 0. I tricked you! The derivative doesn't exist! And you lost a point on a quiz. And it's, you know, that's annoying. So, fair warning. Fair warning. Okay, so, doesn't exist. But, and that was the thing, though. This is indeed a global minimum. It never gets, the absolute value of x does not ever get lower than 0. And it's equal to 0 there. F of 0 is indeed 0. It never gets lower than that. So it is indeed, by definition, a global minimum. But it has no derivative. And so its derivative, it has no derivative at 0. And so this is not true. You cannot come to that conclusion. All right. Oh boy. Oh, this stuff. Okay. More definitions. Here we go. A critical number. A critical number of a function f is a number, call it C, and C has to be in the domain of f. So some number in its domain such that either f prime at C is equal to 0 or f prime at C does not exist. So we just saw that the derivative does not exist for absolute value of x at 0. And so it's a critical number because the derivative doesn't exist there. Okay? Or anywhere else where its derivative is equal to 0. So here's an example. Here's number 38. Find the critical numbers of g of x is equal to the square root of 1 minus x squared. So what do we need to do?
Take the derivative inside the
Oh, okay. So we're going to take the derivative. What's the derivative of this?
1 over 2 times minus 1 minus x squared times negative 2x.
There you go.
Yeah.
Good. You took the derivative of the inside stuff. So let's make this a little bit nicer. G prime of x is equal to, how about just negative x over root 1? Okay. Now, yes, we could set it equal to 0 and find blah, 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 blah. But critical numbers, where does this not exist?
When x equals 1.
Or?
Yeah, or negative 1.
Yeah, and so if you're finding critical numbers, there's a little extra step, right? You have to say, does this thing blow up? Because if it blows up, it doesn't exist, right? If you tried to take the limit and do it, it just wouldn't exist. And so so the way I like to deal with these is if you have something over something, we could say, okay, let's find out where the denominator is equal to 0, which is 1 minus x squared. Square both sides, you get 0 is 1 minus x squared. X squared is equal to 1, so then x squared equals plus or minus 1. And then the other way, we take the derivative, we set it equal to 0. Multiply both sides by the denominator, and you get this, which means, yeah, x is equal to 0. And so the critical numbers are going to be negative 1, 0, and 1, like that.
Yeah.
Those are the critical numbers. Okay. Okay. Your book calls this the closed interval method. I call it obvious logic in that you don't really need to write this in the book. You would have figured this out on your own, but we're gonna just do this. The closed, and mine's modified a little bit. Your book has, it puts the steps a little bit differently. But this is to find an absolute min or max values of a function f on a closed interval a to b. A lot of your questions say find the absolute value of f on, and then it'll give you closed interval. And this is what you're going to do. 1. So remember the extreme value theorem, that you have something on some closed interval a to b. And remember, like the very first thing I said, it might be one of the endpoints. Like that minimum value or the maximum value may have occurred at one of the endpoints. That's certainly going to happen if you have a line, right? So the line y equals x defined on 1 to 5, well, obviously the minimum of value occurs here at that side, and its value is 1. The other one is at 5, where its value is 5. So the way I do it first is I just check, I find f of a and f of b. I check the endpoints first. But we're not done, because if you don't know what the thing looks like if your function was x, you're done, because you found them. But if your function is something funky like this, you check the endpoints, you plug in your a, and you find, okay, that's that. You plug in your b, and you find that that's that, but we don't know about the others. Like one of those may be, it may not be. So what do we need to do?
Take the derivative.
Take the derivative, set equal to 0. So we're going to find the critical numbers. The critical numbers by taking the derivative and setting it equal to 0 and solve. Right? That's what you do. Right? Now, then you plug in the critical numbers. Plug in critical numbers, right? So like, that's what we did here. We had some f of x. We took our f prime of x, we set that equal to 0, and we found that x equals some number c. Right there. We'd probably also find that x is equal to d. Right there. And so what we're going to do is we're going to take those, plug them in.
Wait, but wouldn't it be a?
Yeah. But we don't know, right? If you don't know what this thing looks like, you're just gathering information at this point. This is why I'm taking time to like go through this, because in your head, right, you think, well, I found the one, but we don't know. Then that's the thing about this, is you have to do it with all of them before you figure out, indeed, yes, one's less than the other, unless you know what this thing looks like already. Plug in critical numbers. So like what we're doing here, you would plug in f of c and your f of d. And then whichever ones happen to be, and so in other words, like the final step is compare your results.
Oh, yeah, okay.
So we would have here, you have your f of, there's your f of b here. Here's your f of c. You've plugged all of them in and you say, okay, the biggest one was here, and so that's it. Your smallest one happened to be an endpoint, and so it's right there, right?
Okay. Yeah.
There's also the chance that you have a function that looks like this and you don't know that it looks like this. And so you find your f of a, yep, and you find your f of b. They happen to be the biggest ones, but you don't know that, because when you took the derivative and set it equal to 0, you got a c here and a d here, but you don't know what it looks like, so you have to check them all. This is what I'm getting at. Like you could have figured this out on your own, right? You would have said, well, if I don't know, and it could be at the endpoints, these are the things you obviously have to do to exhaust all the possibilities.
Yeah.
Does that make sense? Okay. Okay, so here's an example of that. And we might be done on time. Wow. All right, so here's an example of using this method. And this is what a lot of your homework is. It says, find absolute min and max of f on the given interval. So again, this is where the absolute or global comes in. It's like on the interval, we're assuming that's the entire domain. Because it might give you something, you know, like a cubic like that, and you're like, well, it has no absolute min or max because it goes on forever, but they're going to give you the interval, so it's like this. And you go, oh, okay, I got you. I see what you're saying. And so, there's number 46. We're to do this to this function. F of x equals x cubed minus 3x plus 1. Yes, it's the same one we saw earlier. And this time we are on 0 to 3. The first thing I'm going to do is, hey, maybe we get lucky. I'm just going to plug in the endpoints. Okay, so f of 0 is 0 minus 0 plus 1. It's just 1. F of 3 is 3 cubed minus 3 times 3 plus 1, which works out to 19. Good. Wow. It took me like 6 minutes to do last night. Okay, so now what do we need to do? We found the endpoints. Maybe there's something else going on in there, right? We don't know, because we don't know that this thing looks like this. Although, I mean, we do because we drew it earlier, and yeah. But I'm not going to waste my time on that. What's the next thing that we do?
Take the derivative. Set it to
Yeah! Alright, so f prime of x is equal to
3x squared.
3x squared minus 3, and we set that equal to 0, and we get, just like we did before, that x is equal to plus or minus 1. So let's plug those in. When f is minus 1, we already did this, and so we got, at minus 1, it gave us a 3. And then at 1, when we plug that in, last time we got a negative 1. Aha. So, what is my absolute max?
19. Or,
And that's how I'm going to write it. I'm going to say my absolute max is this. And I'm going to treat that as one thing. It's nice. It has 2 bits of information in it. That's really cool. Now, what's my absolute min?
f of 1 equals negative 1.
There we go. There's my absolute min right there. And then, and getting in the habit of doing this, like, will save you some time if, like, the question were, what's its absolute max and where does it occur, right? Then everything's right there, you know, instead of having to, yeah. And so, just get in the habit of doing that. Okay, one last one. You're gonna encounter something like, well, actually, I'm not 100% sure. But let's say that it looks like you might encounter something like this, so I wanted to go ahead and talk about it. So let's say you have a function, and I want it to be 3/5 x to the 5th minus 5/3 x to the 3rd minus 2x plus 7. And I want to find all the local maxima and minima, or whatever. Or I have some kind of problem with a min and a max. What do I want to do?
Take the derivative.
Take the derivative. And,
equal.
yeah, alright, so I'm going to take the derivative. What is the derivative of this thing?
3x to the 4th.
Okay, 3x to the 4th.
Minus 5x squared. This is nice.
This is nice.
Minus 2.
It's almost as though I planned it out, man. Okay, and so I set that equal to 0. Do we have a formula for the...
Well, you set x squared equal to a.
There you go.
yeah.
Right? And so don't let, you may well encounter something like this. You set x squared equal to a. Now, we will finish that up, but let's just say for a second, if we had this, how would that be different? Would you do a substitution, or
You could factor out x squared.
there you go, right? That would be a lot easier, because then you just have this. That's easy, because that one's 0, that one's 0, that would give you 5/3. Take the square root of that. That would be nice. But in this case, this has a quadratic form, right? It's like this would be a quadratic if we made this substitution right here. So I'm going to let a equal x squared. And I get 3a squared minus 5 times a minus 2 equals 0. Now what do you want to do?
Factor. You can probably factor it.
Right, and because I made this one up,
Yeah.
you can, right? Now, if you tried and you couldn't, then you would do what?
Quadratic form.
Quadratic, right? And so, but we can. And so I'm guessing this must be a...
3 and a 1, and then
A 3 and
minus
a
and just an
We gotta have a 1 and a 2, I guess. So which one's the 1 and which one's the 2?
We need the 1 we need the 1 opposite the 3. So not that like that
Yeah.
one. Yeah.
This one?
We
No.
need the 2 there, the 1 there.
You need the 2
It'd be
here
3A
and the 1 here.
And then the minus and the plus.
Okay, so that
Wait,
gives
wait,
you
wait.
3a.
No,
Ooh,
oh, my-
right.
no,
Yeah,
no.
yeah. Alright, so let's try the 1 and the 3.
A 1 and a 2, right?
Oh yes, thank you. A 1 and a 2.
Then the minus at the 2.
The minus with the 2, and you're saying a plus here. Let's check. First, gives you the thing. Outer gives you a minus 6, plus 1 does give you a minus 5. Minus 2, plus 1. I'm glad you guys remember how to do this. And so, what does that mean? Now this gives us two equations that we need to solve.
A equals 1/3. Negative 1/3.
A equals negative 1/3,
And
or
A equals 2.
A equals positive 2. But A was x squared.
Yeah.
So x squared is equal to negative 1/3, and x squared is equal to 2, which now gives me
Plus or minus root 2.
x equals plus or minus square root 2, or
Plus or minus.
Wait.
mm,
We have more complex. Imaginary.
it would give you an imaginary number because we take the square root of it, and you get x equals plus or minus I times the 1 over the root 3, so we could write it like that. Now, I'm not sure if you will encounter that in the book. If you do, they might report this as, like, let's say they say find all the extrema of this, all the extreme values, or values. It probably wouldn't ask for that. It would just find the extrema. Critical numbers, I mean. I'm sorry. Find all the critical numbers. In that case, you would do this, and maybe they report this, maybe they don't. I'm not sure what they're going to have. But just so you know, we're dealing with real numbers, so most likely your book's just going to have this. These do indeed make the derivative equal to 0. But if once you do that, you're no longer talking about real inputs and real outputs. You're talking about complex inputs and complex outputs. And so that doesn't mean that it's a maximum in some sense or a minimum in some sense. Because when you're plugging in complex numbers, you're taking complex numbers which have two components, right? It's some point in the plane, a plus I times b, and you plug in a plus I times b, and it maps it to some other point in the plane. Call it c plus d, c plus I times d. And so there's something going on where the derivative is equal to 0, but it doesn't have something to do with a maximum or, well, it does, but it doesn't have something to do with the graph of something having a bump on it. It has to do with, you could think about this. I mean, we don't need to talk about any of this. My point is, you just throw these away. But there's something going on here. And what you could do is you could think about if your inputs are complex numbers to this original function. So we're taking complex numbers z and plugging them in. Z to the 5th, 5, 3, z to the 3rd minus 2 times z plus 7. You're taking all of these numbers, and what this does is it transforms where those points go. So you have all your input values here, and they get pushed to other output values here. Every point gets mapped to a new point in the plane. And these critical values, so when z is equal to plus or minus I over root 3, so where would that be? Right here. Then what, with that being 0, means that those points aren't moving. Everybody else is moving. And at the critical values, which happen to be at plus I over root 3 minus I over root 3, here at root 2, and here at minus root 2, the derivative of this thing is how fast are points moving away from it. And so these points won't be moving fast. They're motion. So like you can kind of think about when it comes to two-dimensional stuff, how fast are you moving here? Well, when you're here at a peak, you're not moving. Your speed is 0. Here your speed is negative. Here your speed is positive. When you're talking about two dimensions, you're saying how fast each one of these points gets mapped to a new point. Now you've done this, you've taken your point A plus IB, you plugged it into F and it got moved over here. Well, these points aren't moving. Kind of. That's one way of thinking about it. Anyway, just so you know, that's neither here nor there. You could forget all of this. And probably even said something wrong at some point. But anyway, but what does that mean for this guy? So if you graph this, this thing looks kind of like this. Something like that. And here at root 2, it has a min or a max. I might have drawn it the other. No, I think it would have to be like this. And then here at negative root 2, it has a local max. But there's nothing else there. And I mean, it doesn't really do that because there's no other ones. It would have found it when we did this. If there was a peak here, it would have been found when we did this and solved. But given that it didn't, then this thing looks like this.
So it's a straight line there, or?
Yeah, it's not really straight. It's kind of canted, I think. Here at 7, it looks like this line right here. So it has a slope of -2 right there.
Okay. Wait.
And you can see that right here. Plug in a 0. And so it's better. Goes. Something like that. And when you plug in a 0 into the slope function, you get 0, 0, -2. Its slope is -2 right here. Another way of thinking about that is it looks like -2.7 right here. So it, right around 0, it looks like the line -2x plus 7. So it goes through here at 7. You can also see that by plugging in a 0 right here. All those guys go away and you just get a 7. But anyway, so it does something like this. Kind of this and it pops up like that. But you could guarantee, because no other numbers popped out, you only got a -2 and a +2. If there was another point, like when I first drew it, I did it wiggly. It can't be wiggly, because that would have been a local max. That would have been a local min, and taking the derivative would have found all of them. So anyway. But yeah, so that's just some stuff to know. You could forget everything about the complex numbers because that is not going to show up unless it does. That's what I'm saying. I haven't gone through every one of these problems. When they ask you for critical numbers, they may very well have the complex numbers in the back. And just so you know, like, yes, technically it does have a meaning. It's not just, you can't just throw those away if indeed you're talking about functions of a complex variable. It does still have a meaning, but it's no longer the highest or lowest point of your function because you're not drawing curves in complex space. You're mapping things and whatever. Okay, that's it.